Have you ever, stopped and really thought about ripples in space-time? That's how we always hear gravitational waves described.
It's the standard picture, definitely.
Yeah.
Messengers from these huge cosmic events.
Right. But my brain immediately goes, well, what is rippling? Seriously, what is space-time? And how does a ripple just travel through nothing? It feels like there's something missing there.
And that's a perfectly valid scientific question. Those conceptual hurdles are exactly why people explore alternatives.
Exactly. So today we're diving into one of those alternatives, something called motion theory. It offers a totally different take on gravitational waves, what they are, how we detect them.
It really reframes the whole thing.
Yeah, so our mission, basically, is to try and get our heads around motion theory's view, see where it diverges from the mainstream, and maybe why it could offer a more, intuitive explanation.
A more coherent picture, perhaps.
Yeah, coherent. Think of this as your shortcut to understanding a potentially pretty radical idea.
And it touches on some really fundamental ideas about reality itself, how these massive cosmic events actually manifest to us.
Okay, so let's quickly recap the standard view first. Black holes merge, bang, space-time ripples outwards like dropping a pebble in a pond.
That's the analogy, yes.
Yeah.
And these ripples eventually reach Earth.
And super-sensitive detectors like LIGO pick up the tiny stretching and squeezing of space caused by these waves.
That's the interpretation. But like you said, it raises questions. What is the space-time fabric? How does a wave propagate without a medium in the normal sense?
And how does it stay so perfect, so coherent after traveling maybe millions, even billions of light years? That seems incredible.
It's a significant challenge, like hearing a whisper perfectly across a noisy stadium. It pushes the boundaries of our intuition.
Totally. It feels like maybe we're missing a piece. Which brings us back to motion theory. So what's the core idea here? What's different?
Well, the really foundational shift is this. Motion theory proposes that everything, absolutely everything physical, isn't just stuff in empty space. Instead, it's all composed of structured, rhythmic motion. Everything exists within a universal medium, a kind of motion substrate.
Whoa, okay, so not empty space, but a substrate of motion.
Exactly. Think of it like an incredibly complex dance where all the parts, particles, planets, galaxies, are defined by their patterns of movement and, crucially, how they synchronize with each other. Stability comes from synchronization.
Huh. That's a big change in perspective. So if everything is motion, what are gravitational waves in this picture? No ripples.
Not ripples in space-time, no. In motion theory, they're understood as synchronization disturbances.
Synchronization disturbances.
Yeah, when something huge happens, like two black holes merging, it's a massive disruption to the established synchronized patterns of motion in that region of the substrate.
Okay, so less like a wave spreading out and more like if two synchronized swimmers crash and it throws off everyone nearby.
That's a good way to think about it. It's a disturbance in the rhythm. And the key thing is, this disturbance doesn't really travel across space like a wave.
It doesn't travel. Then how does it get here?
It's more like a cascade. The disruption in one area forces adjacent areas to resynchronize to adjust their rhythm. This effect propagates, or rather resolves, through the substrate. It's about realignment, not transmission through emptiness.
Okay, that completely changes how we think about detecting them then. If LIGO isn't feeling space stretch, what is it measuring?
Motion theory suggests that LIGO itself, with its incredibly precise mirrors and lasers, is a highly stable rhythmic system within this motion substrate.
Right, it's physical matter, so it's part of this motion dance.
Exactly. So when that large-scale synchronization disturbance finally resolves locally, right there at the detector, causes a brief wobble, a momentary destabilization in LIGO's own internal rhythm. The mirrors shift slightly, not because space stretched, but because their own underlying motion pattern was briefly disrupted before locking back into a stable state.
So the measurement is real, the mirrors move, but the reason they move is different. It's a local effect triggered by a global re-synchronization event.
Precisely. It's a response to a shift in the local synchronization conditions, influenced by the larger disturbance.
Mind blown. Okay, but what about the time delay? We always hear, this signal came from 130 million light years away, implying it took 130 million years to travel. How does that fit if nothing's actually traveling that distance?
That was probably the most counterintuitive part, but it's central to the theory. In this view, nothing did travel for 130 million years.
Nothing traveled.
The synchronization disturbance doesn't propagate in time like that. Instead, it resolves locally. A region of the substrate, like the one containing our detector, comes into alignment with the new overall pattern caused by the distant merger.
So the arrival time isn't arrival time.
Not travel time, no. It's the time it takes for the local system, the detector, to resolve its rhythmic structure in response to that large-scale disruption. The when is about local resolution, not signal travel duration.
So the distance is still relevant somehow, but not for calculating travel speed.
Exactly. The distance influences the overall structure of the synchronization pattern, but the delay we measure is what the theory calls structural phase resolution.
Okay, structural phase resolution.
I think of maybe a complex machine where one part breaks. It takes time for the rest of the connected parts to adjust and settle into a new, stable operating mode. The delay is about that settling time, that re-synchronization time locally.
It's the time it takes for our local part of the universe's machine to click into the new configuration.
That's a great way to put it. It's when our local instrument gets back in tune with the new cosmic harmony.
Wow, okay. That's fundamentally different. Is there a mathematical way motion theory describes this? Like, how do they quantify the wave?
Conceptually, yes. They relate the strength of the event to the rate of synchronization disruption. So if A is the change in synchronization structure and A is how long that change takes.
Then the strength is like A over the speed of the disruption.
Sort of, yeah. It's the intensity of the resynchronization process. And what LIGO detects is related to the gradient of that change as it resolves locally. The wave isn't an object traveling. It's described more like a shifting field of resonance.
Okay, but if nothing's traveling, how does triangulation work? Using LIGO, Virgo, other detectors to pinpoint the source, that relies on timing differences of arrival, right?
Absolutely, a critical point.
Right.
Triangulation still works, but the interpretation of those timing differences changes.
How so?
The synchronization cascade, this resolution process, doesn't happen everywhere instantly. Different detectors being in slightly different locations and potentially different local substrate conditions.
They'll click into the new pattern at slightly different moments.
Exactly. The timing differences aren't because a wavefront hit them at different times after traveling different paths. They reflect the moments of local phase matching, the sequential resolution of the disturbance across the detector network.
So the math of triangulation still works comparing the timing, but the reason for the time difference is local resolution timing, not travel time difference.
That's the core idea. The underlying principle of using timing differences holds, but the physical meaning shifts profoundly.
Okay, I think I'm starting to see the picture they're painting. So stepping back, why argue this is a better explanation than the standard space-time ripples? What are the claimed advantages?
Well, the proponents argue it provides a more, let's say, physically grounded picture. The standard model uses the geometry of spacetime, which is mathematically elegant, but leaves those questions about the physical nature of spacetime and the propagation mechanism unanswered.
Right, the what is rippling question.
Motion theory offers a concrete substrate structured motion and a mechanism synchronization disruption and resolution. It directly addresses what's rippling, the synchronization patterns, what's the medium, the motion substrate itself.
And how coherence is maintained.
Through the inherent interconnectedness and stability of these synchronized structures. It doesn't rely on a delicate wave maintaining form over cosmic distances. And timing, as we discussed, becomes local resolution, not travel.
As the source material put it, the wave is not traveling, it is resolving.
Precisely. It's a fundamental shift from propagation to resolution.
That does seem to tackle those initial nagging questions head on. Now, you mentioned motion theory makes a unique prediction, something beyond standard physics.
Yes, and this is potentially very significant. The theory suggests that the exact moment of resolution at a detector, the arrival time, might be subtly affected by local conditions within the motion substrate.
Local conditions, like what?
Things like fluctuations in the Earth's geomagnetic field, or perhaps strong cosmic electromagnetic interference nearby. These could, in theory, slightly alter the local synchronization environment.
And that could cause tiny variations in the measured arrival times between detectors, variations that aren't just due to the geometry of their positions relative to the source?
Exactly. General relativity wouldn't predict such influences on gravitational wave timing. So, if such subtle, environment-correlated timing variations were ever observed,
that would be evidence supporting motion theory, or at least challenging the standard picture?
It would certainly be something current physics couldn't easily explain, yes. It offers a potentially testable difference.
Fascinating. So, let's try to pull this all together. Motion theory says gravitational waves aren't space-time ripples.
Right. They're disturbances in a universal rhythm, a cosmic synchronization.
And detectors like LIGO aren't passively measuring stretched space. They're actively resolving a local disruption in that rhythm.
Correct. They're part of the system re-synchronizing.
And the timing isn't about a signal crossing billions of light years. It's about when that local resynchronization locks in.
Sync lock time, not travel time.
So the universe isn't being stretched and squeezed by these waves. It's constantly adjusting, retuning its fundamental rhythm.
That captures the essence of it beautifully. It really invites you to rethink everything from the ground up, suggesting motion and rhythm might be even more fundamental than we currently imagine.
This has been, wow, a really mind-bending deep dive. It definitely makes you question those base assumptions about space and time.
And that leads to a final thought, perhaps for you listening. If the universe really operates on these principles of motion, rhythm, and synchronization, what else might that explain? Could other cosmic mysteries, maybe dark matter or dark energy, be related to aspects of this motion substrate or its synchronization? It opens up a whole new landscape of questions about the fundamental nature of reality.
A universe built on rhythm, that's certainly something to ponder.